Hello everyone. In this video I will be explaining lanthanides, which is a part of F block elements, right? Class 12. So to begin with, let us understand what are F block elements. Now we can define F block elements as the elements in which the last electron enters F orbital of anti-penultimate shell. Now last electron can also be referred to as differentiating electron. Means when we are filling electrons, the last electron will be coming into the F orbital of anti-penultimate. Now what is anti-penultimate shell? Suppose this is the nucleus and these many shells are there. This outermost is called as ultimate. Last but one, this one is said to be penultimate. And from outside the third one, okay, that is called as anti-penultimate shell. Ultimate shell, penultimate shell and anti-penultimate. So that means if the electron is entering into the F orbital of anti-penultimate, we will call it as F block element. Now, if we are asked to write the general electronic configuration, the general electronic configuration is N-2 F 1 to 14, because the maximum capacity of F orbital is 14. N-2 F 1 to 14, N-1 D 0 to 1. At times it's D0 also, okay, and NS2. So this is the configuration. When you check the periodic table, first NS is filled, S1, S2 is filled, then one electron goes to D orbital, right, D1, and then in between them there are lanthanides. It's something like this. You have lanthanum, then you have hafnium. Lanthanum is 57 and this is 72. I am talking about lanthanides. This is lanthanides, right? So between them 58 to 71. So these are lanthanides. Similarly, if you talk about actinides, it is actinium. Actinium is 89. And after actinium, the next element here is 104. Right? So between them 90 to 103. These elements are actinides. Okay, so before them S1, S2. So S2 is filled, D1 is filled, and then the next electron is going into F orbital. Right? So NS2, N-1 D, at times 0 also, and in between them F orbital will be filled in them. So the general configuration is this. The F orbitals are also, F block elements are also termed as inner transition elements, because they are lying in between the transition elements. Not actually lying, their atomic numbers are in between. Actually their position is at the bottom of the periodic table. So there are two series which are placed at the bottom of the periodic table. These belong to F block. Right? So what are the series? Lanthanides and actinides. Lanthanides or lanthanoids. Similarly, actinides or actinoids, both are same. 4F series is the name for lanthanides. For actinides it is 5F. Lanthanide involves the filling of 4F orbital and actinides involves the filling of 5F orbital. There are 14 lanthanides and 14 actinides. As I said, atomic numbers 58 to 71 are lanthanides. So 58 is cerium to lutetium, atomic number 71. And actinides are from atomic number 90 to lawrencium 103. Thorium to 103. That is lawrencium. So 14 actinides and 14 lanthanides. Lanthanides, another name is rare earth elements. And all the actinides, these are radioactive elements. Right? And if we want, we can specify, the configuration of lanthanides and actinides separately also. In that, we will have to specify the noble gas. So in lanthanide, xenon, and then 4F 1 to 14, because 4F orbital is being filled. So if this is 4, this will be 5D. And if it is 5D, this will be 6S. Likewise in actinium, actinides, it will be radon, 5F 1 to, it is 5F, then 6D and then 7. Okay, so the general configuration is known. We can also write down the individual configuration also. Right? Now we move on to lanthanides specifically. So in this video I will be completing only lanthanides. For actinoids I will be posting another video. So please watch the video till the end. Now what are lanthanides? The general characteristics we are taking. The first characteristic what we are considering is the configuration. These are the lanthanides. Now, though lanthanum is mentioned here, lanthanum is not a member of F block element. It's a D block element, right? So these are the 14 lanthanides. Their atomic numbers are mentioned here. Now, when you see the configuration, you'll find lot of abnormalities in the configuration. Normally, it should have been D1, and then F should have been filled as F1, F2, F3, and so on. Just see in the first lanthanide, that is cerium itself, there is no F1. There is no D orbital. 5D is 0. Though not mentioned, you can find, in some books they write it as xenon. They write it as 5D 0 and then 4F2 and 6S2. If you omit this also, it is understood that there is no electron present in 5D. So, from the first one, if you check, 6 elements do not have 5D. Just to remember this, you can write 5D 0. That means for the first 6 elements, there is no 5D. And it begins with 4F2, 3, 4, 5, 6, 7. Right? So 1, 2, 3, 4, 5, 6. 6 elements do not have D. The they do not have D means 5D 0 it is. Then, because it has become half filled now, in gadolinium, F is maintained as half filled and 1 electron goes to D. 1 goes to D. And now again D is missing. So this is some abnormal configuration of gadolinium. It has retained as half filled. As per this, it should have been 8 and then D 0. No, it retains half filled and 1 electron goes to D. Again it goes like this. D becomes 0. So this will become 9 now. And 9, 10, again 6 elements do not have D. And again in the last one, lutetium, you will find that 4F14 is maintained. Okay, again 5D1 comes here. Okay, so the elements, these are the elements and these are the names given of various elements. Right? Now, moving on to the next property. Next property of lanthanides, oxidation state. The most common oxidation state of lanthanide, the most stable oxidation state, in fact, you can say, is +3. Though some of these elements also show +2 and +4 oxidation state. But even though they show 4, these elements will have a tendency, suppose it is 3 is more stable, I said. Suppose it is existing in 2 or it is existing in 4, it will have a tendency to become 3. This 4 also will have a tendency to become 3. So if it is 2 oxidation state and it is having a tendency to undergo oxidation, means if any element is in the 2 oxidation state, then it will behave as a reducing agent because itself is undergoing oxidation. If it is in the 4 oxidation state, it is itself undergoing reduction, so it will act as oxidizing agent. So in 2 oxidation state, it will behave as reducing agent, and in 4 it will behave as oxidizing agent. Now if you check the elements out of the elements which we wrote just now, cerium and terbium, they exhibit 4 oxidation state. Because after losing those 4, it is able to get F0 and F7. Yeah, you can just notice this here, cerium and terbium. Check in this table, cerium. So if it is losing 2 here and 2 here, it will become F0. That will be stable for it. For terbium, 2 here and 2 from here, it will become half filled F. So that is also stable for it. So these 2 elements are those which will have a tendency to exhibit 4. Otherwise, all elements will have a tendency to exhibit 3 oxidation state. How 3? Okay, so from here, 2 electrons will be lost and 1 electron from here. Got it? Now, you check it here in this europium and ytterbium. They will have a tendency to show +2 oxidation state to achieve F7 and F14 configuration. Let us check their configuration now. Europium, this one, europium and ytterbium. So if they lose 2 electrons, it will become half filled. This also, if it is losing 2, it is becoming full filled. So they will be having a tendency to show 2 oxidation state. Okay. Yeah, just note this. Please make the notes of the F block element. That is the best thing to remember. So here is the configuration of europium and ytterbium in two oxidation states, 7 and 14. At the same time, lanthanum, gadolinium and lutetium, they will have a tendency to show only +3, because by losing 3 they are getting F0, F7 and F14 configuration. Let us notice this. Yeah, just see what were the elements we said. La, then we said gadolinium, and then we said lutetium. Just see, if they lose these 3, it will become F0. If they lose these 3, it will become 7, these 3, and then F14. That is stable configuration. Okay. Now this part I already told you. If they are in the 4 oxidation state, they will behave as oxidizing agent. If they are in the 2 oxidation state, they will behave as reducing agent. Got it? Now, ionization enthalpy, the next property. The first and the second ionization enthalpies of lanthanides are similar to calcium, whereas the third one depends upon whether they are getting a stable configuration or not. In case by losing one more they are trying to get the stable configuration, then the ionization energy will be low, like lanthanum, gadolinium and lutetium, which I just showed you here. These 3 elements, they will have abnormally low value of third ionization enthalpy. This is third ionization. So these elements will have abnormally low third ionization enthalpy because of the stability of 0, 7 and F14 configuration. Okay, respectively for these particular elements. Now, moving on to the next property, color. All lanthanides are silvery white metals, but many of the trivalent ions can be colored also. Trivalent ions may be having unpaired electron, because the color is dependent upon the unpaired electron. Okay, the color of this arises because of absorption in the visible region. In the visible region there is absorption, and due to which there will be FF transition. Okay, so they will be able to exhibit color, because most of the time the F orbital is partially filled. If it is completely filled, then it is not going to exhibit any color. Got it? The next property we discuss is magnetic property. Now, if the ions are having all paired electrons or no electron, that is if it is F0 or 4F14, then they will be diamagnetic. And even if there is one unpaired electron, mostly there are some unpaired electrons in them, then they will be paramagnetic. And the paramagnetism arises to maximum in this one, in ND. Right? So because it is having the, depends upon the number of the unpaired electrons in them. Got it? So the next property which we are considering is the chemical property. Now chemical property says, like, all lanthanides are highly electropositive. They are all electropositive metals, first thing, and have the chemical properties like we say as lanthanides differ only in the number of the electrons which are there in F4F, because most of them they have S2 and have D1 or D0. So they all will have the similar chemical reactivity. That is very, very important. First thing, they are highly electropositive. Second thing, they will have similar chemical properties. This can be asked, why lanthanides have the similar chemical properties? Because the lanthanides differ only in the number of the 4F electrons. And these 4F electrons are very effectively shielded from the interaction. So that means these electrons will not be able to participate. 4F electrons will not be able to participate. And the number of the electrons which are there in the other orbitals are same in them. Therefore, their properties are same, and the separation from one another is very difficult. That is why we say lanthanides cannot be separated from each other. They cannot be isolated. They cannot be isolated because they only differ in the number of the 4F electrons. That is only different. Rest the number of the electrons in all of them are same. So that is why they cannot be separated. They will have the similar chemical properties. Got it? Now next one. Chemical, what are the characteristics of them? I've just jotted them together. Silvery white metals which will tarnish. It is TAR. Tarnish on exposure to air. That means by reacting with air, they will be forming oxides or hydroxides. Their hardness increases with increase in atomic number. That means when you move from left to right in the periodic table, their hardness will increase. Melting point somewhere lies between 1000 to 1200 Kelvin. They have a typical metallic structure. They are good conductors of heat and electricity. And the earlier members are similar to calcium, whereas the later ones are similar to aluminium. Okay, this is another important point. Their hydroxides are ionic and basic in nature. Second point, the basic nature decreases from the first one to the last one. Though lanthanum is written along with lanthanoids, it is not F block element. Please make sure this point is clear. So if you see which is the strongest base, La, OH taken thrice, and the weakest base is Ln. Right? Lu. This one, Lu. Okay, this Lu, not Ln. Ln is the general symbol written for lanthanides. La is the strongest and Lu is the weakest base. Got it? Yeah, this is, a sort of a flow chart where Ln, this is Ln in the center. Ln is a normal symbol written for lanthanides. So, lanthanoids react with halogen and form LnX3 with water. Ln OH taken thrice, this is thrice, plus hydrogen, this is with carbon, it forms carbide. With nitrogen, it forms nitride. With sulfur, it is Ln2S3. With oxygen, it will form Ln2O3. It is 2 and this is O3. And with acid, they are going to form salt plus liberate hydrogen. So what you find is all the properties of lanthanides are similar to aluminium. We write AlX3, AlOH taken thrice. You can check. All the properties are very much similar to aluminium. Okay. Now, moving on to the next topic, that is lanthanide contraction, a very important topic of lanthanides. What is lanthanide contraction? The steady decrease in atomic or ionic size of the lanthanides with the increase in atomic number. That means when you are moving across from left to right in the periodic table, there is decrease in the size of the lanthanides. This is called as lanthanide contraction. So this is a graph between the ionic radii and the atomic number. When the atomic number increases, their size is decreasing. The size is decreasing. Why? That cause we are going to study now. This is the cause. Okay. Now, what is the cause saying here? The last electron in lanthanides is entering into 4f orbital. And because of the poor shielding of this 4f orbital, it is not able to provide effective shielding. F orbital has a complicated shape. So it is not able to provide the effective shielding. Because it is not able to provide the effective shielding, the atomic size decreases across the period with the increase in the atomic number. So because of the poor shielding of the 4f orbital, in lanthanides the size decreases. And this is also a very, very important question, consequences of lanthanide contraction. There are three main consequences of lanthanide contraction. Number one is 4f and 5f transition series have nearly the same radii, and out of which zirconium and hafnium, they have exactly, almost same radii. Now actually, if you check what is the position, if you see scandium, you have titanium, vanadium, this is okay, this is niobium, yttrium, zirconium, niobium, and you have here tantalum. I'm just drawing one part of the periodic table just to explain. This is 3D transition series, this is 4D transition series, this is 5D transition series. Okay, so what you will find is that in this is 57 atomic number, this is 72 atomic number. So from here to here the size increases. That is not a problem. From here when you come down, because of lanthanide contraction, what you find is, because of lanthanide contraction, the size of this also starts decreasing. When the size starts decreasing, so what you find is, from 3D to 4D, the size increases, but 4D and 5D series elements, so here it should be D, 4D and 5D, not F. 4D and 5D transition series, they have similar radii. Why? Because of lanthanide contraction. Because of lanthanide contraction, this particular series will have small size. So from here, when you come down, you will find 4D and 5D series elements are having same radii. So in that, for particularly zirconium and hafnium are having exactly the same radii. Next point is, it is difficult to isolate. That we have already discussed. They have similar properties and difficult to isolate. Third point, the basic nature of the hydroxide decreases across because the size is decreasing. Size decreases, so the basic nature of the hydroxide also will decrease with the increase in atomic number. With the increase in atomic number. Right? I hope this point is also clear. There are 3 points you will write down. 1, 2, 3. 4D, 5D transition series have similar radii. Number 2, it is difficult to separate the elements in the pure state. Number 3, the basic nature of the hydroxide decreases with the increase in atomic number. And these are some important uses of lanthanides given. Mish metal, this is the composition which is mainly used for making this bullet shells and flinter, lighter flints, and mixed oxides of lanthanides are used as the catalyst. Okay, so these uses you can just go through it, right? So I hope this lanthanoids is clear. In the next video, I will be completing actinides. So with that, DF also will be done. Okay, thank you.